Okay, so again, what I did is I took this equation here, and by multiplying both sides by the least common denominator, I was able to, with cross reducing, I was able to solve for R3. And here we go. All right. Any other questions there? Well, that one. All right, let's look at another one here. This one here is t is equal to the square root of 2s over g. And we want to try to take this formula and solve it for s, okay, the variable s. This formula, out of interest, pertains to a pendulum, okay, like on a clock. And a pendulum is going to sweep out a certain arc length here versus time, okay? So this goes back and forth, a pendulum on a clock. And g is the acceleration of gravity, okay? On Earth, it's 32 feet per second every second, or 9.8 meters per second every second, all right? It's this formula solve for time t. We want to solve it for the arc length here, the length of this arc that this pendulum bob sweeps out. All right, we want to solve it for s. Well, how are we going to get s all by itself? First of all, we have to get rid of this square root. How do we get rid of the square root? So we're going to have to square both sides of this equation, or this formula here. That'll knock out that square root on the right side. Hence, we have t squared is equal to 2s divided by g. Solving for s now, we want to get rid of this fraction here. So I'll multiply both sides by g. And when you multiply the right side by g, of course, it cross reduces out. So gravity's gone there. And so we're left with gt squared is equal to 2 times the arc length s. Finally, we divide both sides by 2, and we got it. We have solved for s. So therefore, s is equal to g times the time squared divided by 2. And there we go. So we solve for s. All right, we solve for s. Yeah, like I said, if you get into computational sciences, you're going to be manipulating formulas all the time. And obviously your algebraic skills are needed to do such a thing. And that's why this is an invaluable survival skill in the computational sciences, or if you go into any engineering area, okay? You have to know how to manipulate formulas. Even in computer science, if you're going to be a programmer, you have to know how to manipulate formulas too. All right, so I'm going to give you a little classwork to play around with here to close the door on section 1.6. So we'll call this classwork 1. Today is the 28th day of September. It seems like September went so quickly. I would like you to solve a couple of equations for me. This first one is going to be 30 times k to the negative 2 power minus 23 times k to the negative 1 power. Plus 2 equals 0. My hint to you here, ladies and gentlemen, is to use a u substitution because this equation is quadratic in form. So my hint is to let u be equal to k to the negative 1 power. That's the hint. U substitution. Reduce this down to a quadratic equation in u and then go from there. All right, number 2. Let's see if you could try this one here. And my hint for you on this one is also utilize the u substitution because this equation is quadratic in form. This degree is twice the degree of this term. So let u be equal to 2 plus 3 over t. There's your hint. Okay. Solve that equation for t utilizing a u substitution for both these here. Okay. All right, try that. And then there's just one more here. If you could take this formula and solve it for V2. And the formula presents itself as T1 over S1 V1 equals T2 over S2 V2. Solve for V2. I'll give you time to work on that. We'll call that classwork number 1. Today, September 28th. Okay. Are we ready to look these over, or? All right, number one here is probably in need of what's called a U substitution to help us to more easily deal with this equation. And the hint was to let U be equal to the middle variable, which is k to the -1 power. Because if you do that, then this would imply that U squared then is equal to k to the -2 power. So upon making these substitutions now into our equation goes from being a quadratic form equation to being reduced down to an ordinary quadratic equation in the variable U. And then to solve this equation, I opted for the quadratic formula. But although you could also factor this trinomial on the left side if you want to do that. But I chose to use the formula where my A is 30, B is -23, and C is 2. So the opposite of B plus or minus B squared of B squared minus 4 times A times C all over 2 times A. My discriminant evaluates to 289, which is a nice perfect square of 17. And so the square root does disappear here. And you're going to have two possible solutions for U, 23 plus 17 over 60, which reduces down to 2/3, or 23 minus 17 over 60, which reduces down to 1/10. But you got to back substitute, ladies and gentlemen. You can't forget to do that. We solve for U. We got to bring back what U is set equal to, namely k to the 1 power, k to the -1 power. But k to the -1 power is really 1 over k. And to solve for k, all you have to do is just take the reciprocal of both sides of this equation. Flip this side upside down, this side upside down, so k is equal to 3/2, and k is equal to positive 10 there. And those should be your solutions. Anybody get those solutions there?
Yeah.
I did.
All right, great, awesome. That's a classic quadratic form equation in need of using a U substitution to reduce it down to an ordinary quadratic equation. All right, any other questions about this problem here? So section 1.7 is entitled linear and compound and absolute value inequalities. All right, the first thing we're going to warm up to, ladies and gentlemen, is how to represent infinite sets of numbers by using what is called interval notation. Interval notation is used in higher level math all the time to represent sets of real numbers, infinite sets of real numbers. And interval notation makes use of open brackets or open parentheses. And then you're going to always have your small number, comma, your large number. And then you're either going to have a closed parenthesis or a closed bracket. So this is the format in general for interval notation. Let's just dive right in here. This is called an inequality statement, and it is to be read as saying x is strictly greater than 2. So any real number that is greater than 2 will be a solution to this inequality. All right, and there are an infinite number of real numbers greater than 2, so there's no way we're going to be able to list all these solutions. Impossible. So one way to represent the solution set is to graph it on the number line. Now, since 2, notice 2 is not in this solution set because 2 is not greater than itself. That's a false statement. 2 is equal to itself, but not greater than itself. So 2 must be excluded from the solution set. To exclude it symbolically using interval notation, when we graph the solution set, we would have an open parenthesis on 2. Parenthesis means 2 is not in the solution set. And then we're going to shade to the right. That would be the graph of all real numbers that are strictly greater than 2. Using interval notation, the smallest value that we could realize in this set is we could get infinitesimally close to 2, albeit a little larger than 2. So we're not going to include 2, comma. And if I go to the right on the real number line forever, what direction am I going in? I'm going in what's called the positive infinity direction, okay? So in interval notation, the solution set to this inequality would be represented this way. This is the interval notational way of saying all real numbers that are strictly greater than 2. Notice the parenthesis next to 2 means 2 is not included in the solution set, as it is not supposed to be. What if I tweak this inequality and write it like this now? Now this is saying x is what? Greater than or
equal to. And that's when you use the bracket.
That's right. X is greater than or equal to 2. Now, the only difference between these two different inequalities is now in this inequality, in this solution set of this inequality, 2 is included, because 2, although not greater than self, is equal to itself. So this is a true statement now. So we must include 2 now in the solution set of this inequality, and to denote that, we have a open bracket on 2, and then we shade to the right. Bracket on 2 means 2 is actually in the solution set. Parenthesis means 2 is not in the solution set. Interval notation, way of representing all real numbers that satisfy this inequality, is open bracket 2 to positive infinity and then a closed parenthesis. That would be the interval notational way of representing the solution set here. All right. Interval notation makes use of parentheses and brackets. This is saying all real numbers that are strictly less than 2, and to graph all such numbers on the number line, we do not want to include 2. Notice our solution x has to be strictly less than 2. It cannot be equal to 2. So in this case, we would have a closed parenthesis on 2 to exclude it, and we would shade to the left. That's the graph of all solutions to this inequality. How do we represent the solution set interval notationally? Well, to the left, the smallest value found in this set, remember it's always small number comma large number for interval notation. The smallest value found in this set is going to be negative infinity. To the left on the number line forever is negative infinity, so open parenthesis, negative infinity, up to 2, and we do not include 2. That's the interval notational way of saying all real numbers strictly less than 2. All solutions less than or equal to 2 now would have 2b in the solution set here, and therefore we would have to actually include 2 by having a closed bracket on 2, and we shade to the left. Make sure you always put arrow at the end of your shading because your solution set is infinite. Okay. Interval notationally, we would have open parenthesis, negative infinity, up to 2, and include 2, hence the closed bracket. All right, is this making sense here, how we're graphing solution sets to inequalities and also representing them using interval notation, parentheses and brackets? Notice an observation to be conscious of is the fact that we never put a bracket next to infinity, whether positive or negative infinity, because infinity is not a number. Infinity is the concept of moving in a particular direction forever, okay? So always put a parenthesis next to infinity, never put a bracket next to positive or negative infinity. All right, in section 1.7 in your textbook, ladies and gentlemen, there's a lot of properties for inequalities. You're not going to have to, memorize all these properties here. Of all these properties, the most important properties that I want you to remember is property number 6 down here. This is of critical importance when we start solving inequalities, to remember this property here. But these properties are all cited in a box in section 1.7. I would recommend that you look over these inequalities and just run them through your mind. But I'm not going to have you memorize all of these. But the last property is by far the one we're concerned with biggest in this section here. And that basically says that if C is some negative number here, say C is less than 0 is to say C is some negative number. And if A is less than B, if I have an inequality, and if I multiply this inequality both sides by this negative number C, this is something you have to try to remember to do. You have to flip your inequality symbol around. So whenever you multiply both sides of an inequality by a negative number, you must remember to flip your inequality symbol around. Otherwise, you will have an error. Okay. Also, if you ever divide both sides of an inequality by a negative number, you must also remember to flip your inequality around. So this is the area of great concern when solving inequalities. Failure to remember this, if it ever occurs, is going to lead to an error. So again, try to remember this one. If you ever multiply or divide both sides of an inequality by a negative number, you must remember to flip your inequality symbol around. So that's the one that you want to try to remember. Okay. But other than that, other than this potential sticking point here, solving inequalities is essentially just like solving equations. We got to get the variable all by itself on one side and everything else on the opposite side. So nothing changes between, you know, our ability to solve equations versus solving inequalities. You just got to keep this in mind that if you ever multiply or divide both sides by a negative number, you got to remember to flip your inequality symbol around. Any questions about that there? Again, you might want to just look over these properties in section 1.7. Just be familiar with some of these properties of inequalities, but this is the big one right here. Make sure you remember this one. All right, it's nothing else. Yeah.
Are you able to, like, I don't know, scan it or like take a picture of that and post it? Because like specifically right now on the Zoom meeting, it's not, like, it's really blurry, so I can't really write it down.
Okay, this is in your textbook. It's an early part of section 1.7. They actually give you a table with all these properties in it. Okay, I literally
Okay, perfect. Thank you.
I literally regurgitated this table from your textbook verbatim. All righty, so it's all
Okay,
there.
thank you.
Just remember, it's property number. The last property you got to be careful with and try to remember. If you ever multiply or divide both sides of an inequality by a negative number, make sure you flip your inequality symbol around. It's that last property you got to be the most conscious of. Okay. All right. So that's armed with all that knowledge. Let's see if we can begin to solve some inequalities now. All right, so here's one right here. This is going to be a rational inequality in the sense that we're going to have fractions present. But I look at it this way: if we can do difficult problems, then all the other ones will probably seem easy. So why not just dive into one that's difficult? All right, so we're going to try to solve this inequality for the variable y for its solution set. And to do that, we eventually have to get y on one side of our inequality, preferably on the left side, and our number on the opposite side. Ladies and gentlemen, think about what we would do if this was an equation. If we had the equal sign here instead of the inequality symbol, what would we do? It's a rational equation. We always try to get rid of the what first? The fractions. And how can we do that? What's the least common denominator of 4, 6, and 12?
12.
Let's multiply both sides of our inequality by a positive 12. And notice, because I'm multiplying both sides by a positive number, I do not flip my inequality symbol around. It's only when you multiply or divide both sides by a negative number must you do that. All right, now multiplying 12 by y plus 3 over 4, the 4 is going to cross reduce into the 12. 4 divides into itself once. 4 divides into 12 3 times. 3 then in turn will get multiplied by quantity y plus 3. Minus 6 divides into itself once. 6 divides into 12 2 times. Minus 2 in turn will get distributed into 3y plus 1. On the right side, these 12s cross reduce out to 1s, and we're left with 1 times negative 1 or negative 1. Does everybody understand how we got rid of our fractions there? By multiplying both sides by 12. All right, now that all the fractions are gone, it's just a matter of solving for y. What would we do next? Pretend it's like an equation. We have to clean up the left side, correct? Quite a bit of simplifying to do over here. We're going to have to distribute a 3 and also a negative 2 inside the parentheses. So we're going to have 3y plus 9. Negative 2 times 3y is minus 6y. Negative 2 times 1 is minus 2. And that's greater than negative 1. Continuing to simplify the left side by combining like terms. 3y minus 6y nets us negative 3y. 9 minus 2 is plus a 7. Greater than negative 1. Now we got it down to a fairly simple looking linear inequality. Subtract 7 from both sides. Trying to isolate y on the left side. 7's drop on the right, leaving us with negative 8 on the 7's drop on the left, leaving us with negative 8 on the right. Finally, we have to divide both sides of our inequality by a negative 3 to get y by itself. But what do we have to do? Do you remember?
Flip the sign.
Yep, because we're dividing both sides now by a negative number, we must remember to flip our inequality around. And again, if you forget that, that's going to be an error. So try not to forget that. We're dividing both sides of the inequality by a negative number. Hence, after doing that, we're going to have just y is less than, negative divided by negative is equivalent to a positive. So y is less than 8/3. And essentially, that's your solution set to this inequality. All real numbers that are less than 8/3 will be a solution to this rational inequality up here. To graph the solution set, we make our number line. I like to put 0 on the number line to establish a reference point. 8/3 being positive will be to the right of 0. You can even turn 8/3 into like 2 2/3 if you want to, but I'm going to leave it as 8/3. Now, am I to include 8/3 in my solution set?
No.
No.
No. Therefore, we have a parenthesis on 8/3, and we must shade to the left to encounter solutions that are less than 8/3. So this would be the graph of our solution set to that inequality there. To represent the solution set using interval notation, you need to always work from left to right when establishing interval notation. So what's the smallest value found in my solution set? Well, that's in the negative infinity direction. So open parenthesis, negative infinity, up to 8/3, but not including 8/3, hence the parenthesis. And that would be the formal interval notational way of representing the solution set of this inequality here. So any questions how we solve this inequality for y? And then represented the solution set using the graph and also the interval notational method there, right? So that's a typical problem you could run into in the future. Solving an inequality for a variable. Just remember, if you ever multiply or divide both sides by a negative, you must flip inequality around. Try not to forget that. That's often forgotten, and it'd be a shame to have to go through all that work and then mess it up at the end by failing to flip your inequality. So try to remember that one there. Okay. Now I would like to show you how to solve what are called compound inequalities. And there's two main types. There's ors and ands. Okay, so this first one is going to be a compound or inequality. And to be an or inequality, you literally have to see the word or. That's a requirement. So you got to see or to have a compound or inequality. If you don't see the word or, then it must be an and. All right, so this is called the compound or inequality. We have two inequalities connected by this word, this disjunction, this word or here. And ladies and gentlemen, the word or suggests that we always take the union between sets, okay? The union between sets. Now, what's this thing called the union between sets here? Now, let me show you with a real simple example. Suppose I have set A to be defined to be the set consisting of these elements, 1, 2, 3, 4. Suppose my set B is another set that consists of the elements of 3, 4, 5, 6. What would be this new set called A union B?
Would it
What
be
is-
3 and 4?
Yeah, what does union do to two sets?
You add it?
Yeah, union actually just joins sets together, literally. It makes sense. To provide a union of two things means to join the two things together. So therefore, A in union with B is going to be a set consisting of all these elements in both sets. So 1, 2, 3, 4, 5, and 6 would be A union B. Okay. So that's what the union of sets does. It joins sets together, whether they have anything in common or not. It just joins them all together in a one big old set. All right. So that's what union does. Okay, so to solve this compound OR inequality here, we're gonna have to solve each of these inequalities individually. So I'll solve this one for X, I'll solve this one for X, and then we're going to join the solution sets together to form the solution set of this entire compound statement here. All right, so how do we solve for X here? I am going to distribute the 3. Combine like terms on the left side, -6 plus 2 is -4. Now it's time to separate the variables on one side versus constants on the opposite side. To do that, I'm going to subtract X from both sides. 3X minus X is 2X on the left side. These X's on the right side drop out, leaving you with -8. Now, continuing to separate, I'm going to add 4 to both sides. So I have 2X is less than or equal to -4. Finally, I divide both sides of my inequality by a +2. And because I'm dividing by a positive, I do not have to flip my inequality around. Some students get this confused. They think, well, wait a minute, we got a negative on the right side being divided by 2. And since we have a negative, we should flip our inequality around, right? The answer is wrong. I'm dividing both sides by a +2. I don't care if we're dividing a negative by a positive, it's what we're dividing by that determines whether we flip our inequality around. Since I'm dividing both sides by a +2, you don't flip the inequality symbol around. Therefore, the solution set to this first inequality in our compound OR inequality is to say that X has to be less than or equal to -2. That's the solution set for the first inequality. But we're not done. We now have to solve for the solution set for the other inequality over here. To do so, I will distribute the 4 inside the parentheses. And combining like terms on the left, I have 4X plus 6 is greater than -2X plus 4. Time to separate the variables on the left versus constants on the right. To do that, I'm going to add 2X to both sides. So I have 6X plus 6 is greater than 4. Subtracting 6 from both sides of the inequality, I now have 6X is greater than -2. Dividing both sides by a +6. Notice I do not flip my inequality around. So I would have X is greater than -2/6. Or you could even reduce that down and say X is greater than -1/3. All right, so what we have to do now is to represent the solution set of our entire compound OR inequality. We have to take the union of these two solution sets, which means we have to join these sets together here. Therefore, we have to find the union of these two sets. And one way to do that is to graph the union or the joining of these two sets together. So what would be the graph of all real numbers that are less than or equal to -2? Well, to graph this solution set on the number line, I would have a closed bracket on -2 to include -2 in the set. And then I would also have to shade to the left to encounter solutions that are less than -2. In union with or joined with all solutions that are greater than -1/3. So I will put what -1/3 a little bit to the left of 0. And notice -1/3 is not to be included in this solution set. You don't have the equal sign here. So therefore, we would have an open parenthesis on -1/3 and shade to the right to include real numbers that are greater than -1/3. So this would be the graph of the solution set of this compound OR inequality here. Okay. As long as we choose a real number that's either in this solution set or this one, it will satisfy the entire compound OR inequality and be a solution to it. So, got a question. Can you give me a solution out of this interval here? Give me a solution, a real number that would be a solution. What's that? Give me a number out of this interval. You said negative? That's all I caught was negative.
-7.
Negative
-7, -3, -3.6, -8.1999999, -2.0000009999999 would be a solution. Do you agree? There's an infinite number of solutions, or real numbers less than -2. -1 million would be a solution. Give me a solution or a real number out of this solution set. Any number greater than -1/3. Give me something.
3.
1 would be a solution. 0 would be a solution, correct? -10 mil, a +10 million would be a solution. All right. Give me a real number that's not a solution to this compound or inequality. That's not a solution.
-1.
Yeah, -1 is in the dead zone. Do you agree? There's no real numbers in this interval here that would be solutions to our compound or inequality. So -1 would not be a solution. Can you give me another number in this interval, this dead zone, that would not be a solution? -1 would not be a solution.
-1/4.
Yeah. Oh, you know what? Let's see. -1/4 would be -0.25, which is greater than -0.3333.
Oh, right. Sorry.
So -1/4 would be tucked in this upper solution set, just tucked in there. Give me another real number in here that's not a solution. -1's not a solution.
-1.9.
Yeah, -1.9 would not be a solution. In fact, how many real numbers are not solutions? How many real numbers are in here? There's an infinite number of decimals. Do you agree? Infinite number of real numbers in here that are not solutions. And there's also an infinite number of real numbers that are solutions, right? Interval notationally, how would we represent this solution set formally? Well, we always start by, to form interval notation, we start on the number line from the left and we work to the right to put together our interval notation. So what's the smallest number found in the solution set? The smallest number is -what? Infinity. Do you agree? -infinity. So here we go. Open parenthesis, -infinity, comma, up to -2, and I include -2, hence closed bracket. In union with, you now need to use the union symbol because or means union. We need to join this set now and pick up with this solution set, not including 0, comma, up to positive infinity, closed parenthesis. That would be the interval notational way of representing all solutions to this inequality. Everybody see that there and understand
Wouldn't
that?
it be
Wait, where's the-
-1/3?
Wait a minute, you're right. Why do I got 0 in there? Yeah, sorry about that. -1/3 is the furthest to the left that we could fathom, which we could never actually have -1/3, but we could get infinitesimally close to -1/3. Yeah, this should be -1/3 here. All right, so this would be -1/3. -1/3, comma, up to positive infinity. But again, make sure you don't include -1/3 though. All right. Is that making sense, ladies and gentlemen, how we solve this compound or inequality here? And then in the end, we had to take the union of their solution sets, join them together, literally. Okay. So that's a classic compound or. And this is being recorded. So like I said, if you missed anything, you know, you'll be able to look at this at your leisure. Heck, you can even look at this at 2:30 a.m. in the morning if you want. If you can't sleep, you get up and watch. You can watch me. Okay. Let's try this one. I'll probably be sleeping though, hopefully. All right, how about this one here? We want to solve this compound or inequality. And so what we're going to have to do is solve each of these individually and then take the union between their solution sets. Okay. All right, so let's solve this one first. By doing so, we are going to subtract 1 from both sides. M is less than or equal to 5. That's the solution set for the first one. Or now we have to solve this inequality for M. I would multiply both sides by 3 to knock this fraction out here. Multiplying the left by 3 and multiplying the right by 3. Wait a minute, do I flip my inequality around? I'm multiplying both sides by something.
It's not negative.
Yeah, I'm just multiplying both sides by a +3, so do not flip your inequality. Therefore, 3 times 1/3 M is going to be M less than 3 times -2 is -6. And there you go. Okay, so let's put together our solution set now. Because or means we need to join these sets together. So let's graph all real number solutions that are less than or equal to 5. Sometimes by graphing these on number lines that are basically stacked up on top of each other, it might be more helpful to see what the union of the sets might be. Okay, so I'm going to do that here. I'm going to graph the solution set of my first inequality as being all real numbers less than or equal to 5. Hence, I will put a bracket on 5 and shade to the left. That's the graph of all real number solutions that are less than or equal to 5. Keeping my tick marks lined up for comparative purposes, I now will graph the solution set of the second inequality, which says the solutions are all real numbers that are strictly less than -6. So not including -6, and we shade to the left. Now, ladies and gentlemen, can you see the union between the graph that would represent the union of these two solution sets? So envision merging these two number lines together. What would be the union or the joining of these solution sets together? Can you see what it would be? So what would be
Wouldn't
the
it just
graph?
be equal to or less than 5?
Yeah, that's the thing. I mean, if you bring these number lines together and join these two solution sets together, notice you're going to have all real numbers that are less than or equal to 5. Okay. Because look at, although -6 is not in the second solution set, it is in the first one. You must include it. So therefore, you are correct. The graph of the union of these two solution sets literally will be all real numbers that are just less than or equal to 5. That's it. That's what the joining of these two sets would represent right there. Using the interval notation, we would represent the solution set from -infinity up to 5 and including 5. And that would be your interval notation, a way of representing the solution set to this compound or inequality here. All right. Any questions about how we solved that and how we took the union of the two solution sets to form the compound or solution set?
I have a question.
Yes.
So you just took it and basically said, okay, well, you merge the two solutions together to get just one interval notation.
That's right. Yeah, because, you know, I mean, when you merge these number lines together, bring them together, you know, this is going to mesh up with this. Do you agree? This is going to mesh up here. And although this solution set's not to include -6, or doesn't care, or says as long as the real number comes from either this interval or this interval, it will be a solution to the whole thing, the whole or statement. And so that's why we also include -6, because this solution set includes -6. So why not just say it's all real numbers less than or equal to 5? Do you agree? And call it a day, right?
Yeah.
Okay. All right. Okay, so we solved a couple of compound OR inequalities for you. And to be an OR inequality statement, you literally have to see the word OR. What if you don't see the word OR, though? Well, if you don't see the word OR, ladies and gentlemen, then you have what is called the compound AND inequality. And there's two types of compound AND inequalities. You have what's called an implied compound AND inequality, and you have what's called an explicit compound AND inequality. And I'm going to show you one of each type, okay? All right, so this first one here is going to be called an explicit compound AND inequality. We call it an explicit compound AND inequality because we literally see the word AND separating the two inequalities that need to be solved. So this is an example of an explicit. We call this an explicit compound AND inequality. To solve for this compound AND inequality, we need to understand what AND means. OR meant union. Do you agree? You know what AND means? AND, ladies and gentlemen, means intersection. And this is the symbol used from set theory that represents intersection. So suppose I have these two sets, A and B again, and I want to form the new set called A intersect B. So what is the set going to be that's A intersect set B? Well, as the word intersection implies, intersection, think of it as being like a north-south road and an east-west road. Do you agree that they both the roads share a common pavement called the intersection right here? All right. So intersection means we take only what's common between both sets and throw them into the intersection set. So what elements are common between sets A and B?
3 and 4.
So only 3 and 4 would be found in A intersect B. Everybody see that there? So notice union's a lot different than intersect. Union means we join the sets together. We just throw all the elements from each set into one big old set. Intersection means we only throw into our set elements that are common between both sets. That's it. That's the difference between union versus intersection. All right, so in the end, when we solve these two inequalities, we're going to have to intersect their solution sets to find the solution set of the compound and inequality. How do we solve for n here? We just add 6 to both sides. I get n is greater than 7. And now we have to solve this inequality for n. And to do so, I'm going to multiply both sides by 4 to first of all maybe knock out this fraction. Since I'm multiplying both sides by a positive 4, we do not flip inequality around. The 4's dive out on the left side, leaving you with 3n greater than or equal to 24 on the right. Divide both sides by a positive 3. Do not flip inequality. Dividing by a positive, and there you go. So what we have to do now is to put together the solution set to our compound and inequality. We have to take the intersection of these two solution sets. And you know, a way to do this nicely is to graph both solution sets on number lines that are oriented vertically, one on top of the other one. It's easy to see what the intersection would be if you do this. To graph all real numbers that are greater than 7, I'm going to put 7 up here. I would have an open parenthesis on 7, and I shade to the right. Now I'm going to graph all real number solutions that are greater than or equal to 8, keeping my tick marks lined up on my number lines here for comparative purposes. Notice I must include 8 by putting a bracket on 8, and I would shade to the right. Now I have a question for you. If you were to merge these two number lines together, bring them together as one number line, where would the overlap between the solution sets exist? The overlap. As I want to intersect these two solution sets.
Thing greater than 8.
Yeah, if you bring these number lines together, the only portion of these solution sets that are in common would be all real numbers that are greater than or what? Equal to 8. Do you agree? That's the only overlap that exists, is right in here. Notice there's no overlap for this portion of the solution set with the other solution set. So the graph of the intersection of these two sets is going to be all real numbers just greater than or equal to 8. That's it. So therefore, to represent the solution set of this compound and inequality using interval notation, I would have an open bracket 8 comma up to positive infinity. And that would be the solution set. So do we understand the difference between or versus and? And takes only the intersection of solution sets. Or would join these sets together. What would be the union of these two solution sets if I wanted the union instead of the intersection? Then it would be all real numbers that would be what? Strictly greater than 7. Do you agree? That would be the or the joining of these sets together. But we wanted and intersection. That's why it's all real numbers greater than or equal to 8. Any questions how we solve this compound and inequality here? Again, this is called an explicit compound and inequality because we literally see the word and. All right. All right. So that's called an explicit compound and inequality. I'm going to now show you what is called an implicit and. An implicit compound and inequality. With an implicit compound and inequality, you do not see the word and. Well, wait a minute. If I don't see the word and, then how do I know it's not a compound or inequality? How do I know this is not a compound or inequality?
It doesn't say or.
I don't see the word or. And if you don't see the word or, then it either has to be an implicit compound and inequality, or it must be an explicit compound and inequality. It has to be one of those. This is called an implicit compound and inequality because we don't see the word and. And yet, the way we read this would still inject the word and into the situation, because this is how I would read this. This is to be read as 3x plus 9 is greater than or equal to -6, and at the same time must be less than 0. That's how you read this. Read it again. -3x plus 9 must be greater than or equal to -6, and at the same time, it must be less than 0. It is an implied compound and inequality. Now, solving compound and inequalities is pretty simple. The most efficient way to do so is just to get the variable all by its lonesome in between the inequalities. So how would I move in that direction? How do I start stripping this middle down to eventually x all by itself? What would I do first here?
Subtract 9.
Yeah, let's subtract 9. Let's subtract 9 from the middle, subtract it from the left, subtract it from the right. When we subtract it from the middle, the 9s drop out. Notice I don't flip my inequalities around because I'm not dividing or multiplying both sides by a negative number. -6 minus 9 is -15, and 0 subtract 9 is -9. Good. Now, how do we get x by itself in the middle? What do I got to do now?
Divide -3.
That's right. Because I'm going to be dividing by a negative, we must flip inequalities around. Because I'm dividing this by a -3, dividing this side by a -3, and dividing this side by a -3, you got to remember now to flip both inequalities. They both must flip around. And if you don't do that, you're going to have an error. All right, so therefore we have x is less than or equal to 5, right? And at the same time, x must be greater than 3. Now, an equivalent way of writing this compound and inequality is to flip the whole statement around. So watch this. I claim that this statement is equivalent to as if I write it like this. X is greater than 3 and at the same time less than or equal to 5. Do we all agree that this and this are saying the same thing? They're saying the same thing. Do we all buy that?
Yes.
Yes.
Okay. I wrote it this way because I like to have my smaller number on the left, larger number on the right, because that sets us up easier for interval notation. Now, to graph this solution set, here's my number line. Here's 0 for reference, 3 and 5. The solutions to this implied compound and inequality is going to be any real number between 3 and 5, not including 3, but including 5. So I will have a parenthesis on 3, a bracket on 5, and I will shade in between. And you have the graph of all real number solutions to this implied compound and inequality. To represent the solution set using interval notation, I work from left to right on the number line. So not including 3 up to 5 and including 5. There's your interval notation. Any questions how I solve that implied compound and inequality there?
I have a question.
Yeah, go ahead.
So the 3 connects with the 5 because they're both correspondingly 3 is a
Because my solution x has to be a real number that's between what? It has to be greater than 3 and at the same time less than and equal to 5.
oh,
So that's why our solutions have to be any number in between what? 3 and 5, correct? In between 3 and 5. That's why we graphed it the way we did. Does that answer your question or?
yes, it does.
Oh, sure. All right. Okay, now that that's out of the way, ladies and gentlemen, I showed you how to solve some linear inequalities. I showed you how to solve some simple ones and then some compound ones, ors and ands. And ands come in two types, explicit versus implicit. Or means union, and means intersection, correct, of sets. All right, and now to wrap up this section here, there's one more topic, how to solve what are called absolute value inequalities. All right, there's two main types of absolute value inequalities. You have what are called your and types, and you have your OR types. Let's look at the AND types first. An AND type of absolute value inequality is going to be one that looks like this. You're going to have the absolute value of X or some expression in X, or it could be some other variable, less than or equal to some real number C. Now, for the sake of our argument, this number C is always going to be a non-negative real number. It's always going to be a positive real number here, okay? So if I have the absolute value of X or some expression in X less than or equal to some positive real number, ladies and gentlemen, this represents what's called it's going to be an implicit, an implied compound and inequality solution set for these types of absolute value inequalities. So the solution set for such an inequality, it looks like this, is going to have to have us taking what's inside the absolute value, in this case it's X, and we're going to have to take that and set it greater than or equal to the negative of this number on the right side, and at the same time it must be less than or equal to the positive of this number on the right side. So the solution set to such an absolute value inequality as this must be an implied compound and solution set. X must be greater than or equal to negative C, and at the same time must be less than or equal to positive C. Or you could just have the absolute value of X is just less than some positive real number C, in which case the solution set will be similar to this. It'll be whatever inside my absolute value symbols will be greater than the negative of the C, and at the same time less than positive C. So when you have your absolute value of a variable or variable expression is less than or equal to or just less than some positive real number, the solution set must always take on this implied compound and look like that. Okay. All right, that's how and inequality absolute value inequalities work here. Now I'm going to show you the OR type. All right, what does an absolute value inequality look like if it's an OR type? Well, it's going to be the absolute value of X or some expression in X, or again, it could be some other variable or variable expression, greater than or equal to C. If the absolute value of a variable or variable expression is greater than or equal to some positive real number, then your solution set must take on an OR compound look to it. So now our solution set would have to look like this. It would have to say whatever's inside my absolute value symbols, in this case it's X, X would have to be less than or equal to negative C, or, yep, that's right, you actually have to see the word or X has to be greater than or equal to positive C. That's what the solution set would have to look like for one of these types of absolute value inequalities. Or you could just simply have the absolute value of X is greater than some positive real number C, in which case your solution set would also have to be an OR. X would have to be less than negative C, or X would have to be greater than positive C. So there you have it, ladies and gentlemen. In general, there's two main types of absolute value inequalities. You have your AND types, where you have less than or equal to, or just less than some positive real number, in which case your solution set takes on an implied compound and look. Or you could have the other type, which is an OR type of absolute value inequality, where you have the absolute value of a variable expression greater than or equal to some positive real number, or greater than a positive real number, in which case your solution set takes on the OR look, where you have to have the word OR. All right, any questions about the two main types of absolute value inequalities here? AND type versus OR type in general. All right, so yeah, I would definitely memorize, the OR types and the AND types. Remember, OR types is variable on left, less than or equal to some positive real number. OR type is variable on left, greater than or equal to some positive real number. Okay, that's the major distinction between them. That would be great if it was that simple, but unfortunately, we do have what are called some special cases. So I'm now going to run you through some special cases that it would probably be wise to be familiar with or even memorize or put them on your note card if you cannot remember them. They're called special cases. If, ladies and gentlemen, if I have the positive absolute value of X or some expression in X less than some negative number, What do you think the solution set to such an absolute value inequality like this is going to look like? Think about it. Can you ever take the positive absolute value of anything and generate anything that's less than a negative number? Well, to be less than a negative number means that this quantity would have to be negative. Can you ever take the positive absolute value and generate a negative? Is that possible? That is not possible. So if you ever have an absolute value inequality that looks like this, you need go no further with it. All you have to do is just say this has no solution. That's your answer. Or we would say the solution set is empty. Empty solution set. Or, ladies and gentlemen, there's a symbol called the empty set symbol. Comes from set theory. This means the solution set is empty. All these representations represent no solution to such an absolute value inequality. If you have the absolute value of x, the positive absolute value of x or a variable expression in x is less than or equal to some negative number, again, there would be no solution to this situation also. Think about it, because could you take the positive absolute value and get a value that's less than a negative number? The answer is no. Could you take the positive absolute value of something and get something that's equal to a negative number? Answer is no. No solution to this type. Here's another special case. What if you have the absolute value of x or a variable expression in x that is greater than a negative number? What do you think the solution set looks like for this type of absolute value inequality? If you take the positive absolute value of something, you're always going to get a positive. But isn't a positive always greater than a negative number? That's always true. So it doesn't matter what you throw in this absolute value for x, it's always going to walk out of these absolute value symbols as being a positive. So your solution set for this absolute value inequality is all real numbers are solutions. To represent the solution set interval notationally, we would represent it by saying our solution set is all real numbers from negative infinity up to positive infinity. That is the solution set. That's a compact way of saying the entire real number line would produce solutions to such an inequality. All right. Another special case. If you have the absolute value of x or an expression in x is greater than or equal to a negative number, your solution set again is all real numbers. So this has an infinite number of solutions, namely all real numbers from negative to positive infinity. By the way, positive infinity does not have to be preceded with a plus sign. If you don't have a sign in front of infinity, it's understood to be positive infinity. Another special case, if you have the absolute value of x is greater than or equal to 0, again, solutions to this are going to be what? All real numbers. All real numbers are solutions. Think about it. It makes sense. When you take a positive absolute value of something, you get a positive. Isn't a positive quantity always greater than 0 or even equal to 0? If we took the absolute value of 0 itself, you would get 0, which is equal to 0. That's why it's all real numbers for this scenario. There's one other case here. If you have the absolute value of x being less than 0, what do you think? To say that a quantity is less than 0 is to say that it must be negative, must be a negative quantity. Well, there's no way you can take a positive absolute value of anything and generate a negative. So there would be no solution to this situation here. And there you go. I have shown you some special cases, ladies and gentlemen, that you at least want to be familiar with. Okay, these are special cases. If you ever run into them, you don't have to go through any formal solution process. All you gotta do is slam on the brakes and say one of these things. Okay. All right. Well, let's just start working on a couple. See if we can solve some of these things. So let's try this one here. I have 2 times the absolute value of 7 minus y plus 1 is less than 17. I want to solve this absolute value inequality. Whenever we solve absolute value inequalities, we always want to isolate the absolute value on the left, on one side of our inequality. So always remember to first isolate your absolute value. All right. So how do we do that? We got to get this absolute value by itself. We're going to subtract 1 from both sides. The 1 dives out on the left, leaving you with this. And we have 16 on the right. Dividing both sides by 2. A positive 2, notice I'm dividing by a positive. We do not flip our inequality. But always be ready for that in case I slip one in like that. And then we got our inequality looking like this. All right, ladies and gentlemen, is this one of our special cases here? Is this one of our special cases here? To say the positive absolute value is less than a positive number? No, we don't have that case. It's not a special case. Okay, so it's not a special case. All right, since it's not a special case, what type is it? Is it an and or an or? Or an and or an or? And or or?
And.
It's less than positive 8. Less than positive 8. It's an and. So therefore, your solution set has to take on this form. So whatever's inside my absolute value symbols would go right here. And my number on the right side would have to go in here and here. So therefore, the solution set of this and absolute value inequality is to say that 7 minus y has to be less than 8 and at the same time greater than negative 8. There we go. This is now the way our solution set to this absolute value inequality must look. And again, I followed literally along with this. Since we have this form, our solution set must take on this look. And that's why it has this look. Now we got to solve for y. This is an implied compound and inequality. We got to get y all by itself in between inequalities. So I'll subtract 7 from all sides. So I have negative 15 is less than negative y and at the same time less than 1. Finally, I got to divide all sides by a negative 1. Notice, since I'm going to divide both sides by all sides by a negative, I must flip inequality symbols around. Got to flip this one, got to flip this symbol around. So therefore, positive y now is going to be less than 15 and at the same time greater than negative 1. I like to have my smaller number on the left and larger number on the right. So I'm going to flip this whole statement around and I'll still have an equivalent statement to say that y is greater than negative 1 and at the same time less than 15. These are saying the same thing. Now we can graph our solution set. If I wanted you to graph it, the graph would look like this. All solutions must be real numbers strictly between negative 1 and 15. So we have parentheses on 15 and we shade in between. Interval notationally, my solution set would be open parenthesis, not including negative 1, comma, up to 15 and not including 15. And we're done. Does everybody understand how we solve this and type absolute value inequality? And type. Let me see how we did that there. Okay, that's an and type. That's a classic and type. All right. All right, I will now show you how to solve a or type of inequality. And here we go. So we're going to try to solve we'll try to solve this one here. All right, we will attempt to solve this absolute value inequality for x. To do so, we want to try to isolate our absolute value on the left side. So to do that, we subtract 5 from both sides. So I minus it from the right, minus 5 from the right, left and the right. The 5s drop out on the left, isolating my absolute value, which is now greater than or equal to, but 4 minus 5 on the right nets me a negative 1. Ladies and gentlemen, before you go further with such an absolute value inequality, you need to check it with your special cases. Is this by chance a special case? To say the positive absolute value is something that's greater than or equal to a negative number. Is it a special case?
Yes.
Right, here it is, right here. The positive absolute value of something is greater than or equal to a negative number. It's a special case. So therefore, we don't have to go any further with this. We slam on the brakes and say our solution set is all real numbers, and we're done. The solution set is all real numbers. If you're to graph all real numbers on the number line, it's basically going to be the whole real number line graph, or it's going to be from negative to positive infinity. Okay, so we're done with that one. Like I said, that's why it's wise to know these special cases. Otherwise, you're going to be doing some unnecessary work. All right. For a situation like this, you're going to think it's an or. You're going to go through the whole, spiel of dealing with the or when you don't even have to deal with that because it's a special case. So yeah, I would definitely, at least be familiar with some of these special cases here or put them on the note card. Okay. All right. Let's try one that is not a special case though. And here we go. Let's try this one. Let's try to solve this absolute value for the variable t. Okay, so we're going to try to solve this absolute value inequality for t. To do so, we isolate absolute value on the left side by adding 9 to both sides. I get this, and then I divide both sides by a positive 5. Notice, don't flip inequality around because I'm dividing both sides by a positive. And now our absolute value inequality looks like this. Notice this is not one of our special cases, and therefore, because it's not a special case, we need to address whether this is an and or an or. What type is it to say the absolute value of a variable expression is greater than or equal to a positive number? Greater than or equal to a positive number suggests it's a what? It's an or, correct? So our solution set must take on this complexion. So we drop our absolute value, and what's inside our absolute value has to take the place of the x here, and our number on the right side has to go in here and here. So therefore, the solution set we have to put together for this or absolute value inequality is to say that t plus 1 is less than or equal to -1, or t plus 1 is greater than or equal to 1. And there you go. So that's what your solution set for this or absolute value inequality must look like. And now we just have to solve this compound or inequality. And we showed ourselves how to do that about a half hour ago. So how do I solve for t here? Subtract 1 from both sides, and t is less than or equal to -2. In union with, or means joining sets together, remember. Now we solve this inequality for t, and we get t is greater than or equal to 0. So ladies and gentlemen, what would be the graph of the union of these two sets here? Can you envision what the graph would be? Well, it's going to be all real numbers that are less than or equal to 2, so a bracket on -2 and shade to the left, in union with all real numbers that are greater than or equal to 0, so bracket on 0, shade to the right. There you go, that's the graph. Interval notationally, how do we represent the solution set? Work from left to right to establish interval notation. So working from the left, which is the negative infinity direction, we would have negative infinity, comma, up to -2, including -2, hence bracket, in union with, picking up with this solution set, including 0 up to positive infinity, closed parenthesis, and that would be your interval notational rendition of the solution set to this absolute value inequality. Right. So I have a question for you. Do we understand, ladies and gentlemen, how to identify whether we have an or an and absolute value inequality? It comes down to how the inequality is oriented with respect to your absolute value. If your absolute value of a variable is on the left, the less than or equal to or less than suggests it must be an and structure for your solution set. If you have a greater than or equal to some positive real number or greater than, your solution set must take on an or look. Okay, so 2 main types. And then what it comes down to now is with practice, you will start to hopefully assimilate all of this, but it's only going to come through practice. And I would also recommend strongly that, ladies and gentlemen, you also maybe peek at some of the examples in the sections that I go over. I think by going over the examples in your textbook, it's only going to help further cement all this material in your mind. I think it's critical to look at examples. I think it's also critical to supplement the problems I give you on ALEKS with maybe a couple of extra practice problems at the end of each of the sections that I go over. There's a wealth of extra practice in your textbook. I would definitely try to do some extra practice. You know, and if you get stumped, I give you all the solutions to the odds and the evens. They're all there on Canvas. All right, they're all there. Just couple more things before I turn you loose on your last classwork here. What if I had this right here? What if I had x is greater than -3, or x is less than 7, less than or equal to 7? I have a question, ladies and gentlemen. What would be the union of these two sets if I join these sets together? Well, I'll tell you what. If you're having a hard time seeing the union, graph these separately on number lines that are arranged vertically relative to each other. You can keep your tick marks lined up for comparative purposes. Okay. All right, let's graph all real numbers that are strictly greater than -3. Well, that's going to be a parenthesis on -3, and we shade to the right. Now, what would be all solutions that are less than or equal to 7? Well, that includes 7, so we have a bracket on 7 and shade to the left. Question, now, what's the union, the joining of these sets together? What would it look like? What would it look like if we take the union of these two sets? Merge these number lines into one number line. What would the solution set look like?
Would it just be all real numbers except for
got it.
-3?
No,
Just all real numbers? Okay.
Yeah, it includes -3, because although -3 is not in this solution set, what it is in this one, correct? So we still have to throw it into the set. You're right. If you merge these number lines and form one solution set of the merging or the joining of these sets, it's literally going to be all real numbers. Isn't that true? It's the entire real number line. That's correct. And therefore, to say x is greater than -3 in union with x is less than or equal to 7, what is the interval notational way of representing this? It's just to say from what to what? Negative infinity up to what? Positive infinity. That's saying all real numbers. Okay, so I just wanted to show you that there. Everybody see that there? All right, I want to show you another one. What if you end up with a compound explicit and inequality that looks like this? What if I said x is less than or equal to -4 and x is greater than 3? And means what? We do what with the sets, solution sets? We intersect them. Don't take the union, we intersect them. So what's the intersection of these two solution sets? Well, I'll tell you what, let's graph them individually on number lines that are arranged vertically, stacked up on top of each other so that we can accurately compare things here. Line up tick marks, keep them lined up. We got 3, and we got 3. How do we graph all real numbers that are less than or equal to 4? We would put a bracket on -4, and we would shade to the what? Left, correct? How do we graph all real numbers that are strictly greater than 3? Parenthesis on 3, shade to the right. Now, ladies and gentlemen, merge these two number lines, bring them together. And if you bring these number lines together, what's the intersection of these two number lines? The intersection. Is there anything in common? Any real numbers in common between both these sets? Anything in common? Any overlap between these solution sets? The answer is absolutely what? Not. There is no overlap. There is no intersection of these two sets. And therefore, we would say that x less than or equal to -4 intersected with x greater than 3. We would say that it's the empty set. The intersection of these two sets is the empty set. There is nothing in common between both these solution sets. Any real number that's less than or equal to -4, you will not find it in this set of real numbers that are strictly greater than 3, and vice versa. Not going to find anything. So yeah, the intersection is the empty set. So if you ever run into a situation like this, okay, you just have to say empty set. All right. And this is called the empty set character that is used in set theory. Okay, empty set. All right, any questions before I give you your last classwork? All right, well, this is the last one here, so enjoy this one. Let's do. Yeah, okay, so let's see if you can do this here. This will be classwork 2. I want you to, solve these things here. So number 1, Negative 11 is less than or equal to 5 minus the absolute value of 2 times p plus 4. See if you can solve this absolute value inequality. And I would like you to graph the solution set and also represent the solution set using interval notation. Okay. And number 2, see if you can solve this. I'll give you a hint. This is going to be a compound, implicit compound and inequality. So see if you can solve this implicit compound and inequality. All right, I'll give you time to work on those things there, and we'll wrap it up. All right, what's weird about this first absolute value inequality that I gave you is notice that the variable is on the right side of the inequality. I just thought I'd throw a little loop into the situation, ladies and gentlemen. That probably caused, hopefully it didn't cause any consternation, but if it did, what you want to probably do is flip the whole statement around first. Flip it all around, and therefore you now have the inequality oriented properly so you can identify, what's going on here. So by flipping the whole statement around, it's still equivalent, still the same old statement. And we discover as we isolate the absolute value now, we're also, we subtract 5 from both sides and then have to divide both sides by a negative. So we're going to have to flip our inequality symbol around here because you're dividing by a -1 here. And now you realize that we don't have a special case. So it is a what? It's an OR type absolute value inequality. Wait a minute. That's not an OR, is it? This is not an OR. It should be a what?
And
Yeah, it's an and. It's an and. That's right. It's an and. My bad. So therefore, it is an and. Absolute value inequality here. So therefore, your solution set must take on this look. 2p plus 4 must be less than or equal to 16, and at the same time greater than or equal to -16. It has to take on that look. Solving this compound implied and inequality, we subtract 4 from all sides, try to get p all by its lonesome in between the inequalities. We now have 2p is less than or equal to 12 and greater than or equal to -20. Divide all sides by a 2. We do not flip inequality around. We get p is less than or equal to 6 and at the same time greater than or equal to -10. Therefore, your solution set to this thing, if you were to graph it, would be all real numbers between -10 and 6 inclusive, including the endpoints. That would be the graph of the solution set. Interval notation would have me writing the solution set this way. And there you go. Did anybody get this solution set for the first one here?
Yes, I have that.
All right. Yeah, this
Yeah,
is a tricky one. It's tricky because it's not even oriented the proper way that I've been showing you. So I kind of slipped that in to see like if you'll be able to handle that. You want to flip the whole statement around, and then by dividing ultimately both sides by a -1, it becomes ultimately an and type of absolute value inequality. Solution set of which then must take on this structure. Solving for p, we do get eventually that. Okay, so that one's good. The last one is an implied compound and inequality, and I want you to solve it for x. So we want to try to get x all by its lonesome in between the inequalities. First thing to do is knock out this fraction by multiplying all sides by 3. So we're going to multiply all sides by 3. Notice we do not flip inequalities around. We're multiplying by a positive. We end up with this. Then I'm going to add 1 to all sides, get it down to this. Divide all sides by a +4. Notice, no need to ever flip the inequalities around. And we finally get it down to this. Therefore, the solution set of this implied compound and inequality would be all real numbers between -5/4 and +4 inclusive. And interval notationally, that would be the solution set. Anybody get this?
Yes.
yeah, I did.
Okay, all right. All right, ladies and gentlemen, that is it. I'm going to let you go. Like I said, I will open up the chapter 1 quiz on Alex. I will open up the first exam on Monday, and the session on Monday is set aside for your use. Okay, so if you have any questions, you can bring those questions to me. If you don't have any questions on Monday, even if you want to just log in briefly, just to, have it show on the report that you did log in, I will not mark you absent. Okay, so Monday is set aside for your questions. If you have any questions about material for the first exam, or you're stumped on any questions regarding maybe this stuff I went over today, I'll be happy to answer any questions for you. Okay. All right, and I will send out an email confirming that the exam is due by midnight, October 4th. So when is your chapter R and chapter 1, Alex, homework and quizzes due? When's that stuff due?
October 3rd.
Yeah, it's due by midnight, October 3rd, Monday, midnight. Okay, so hopefully you've been keeping up with Alex and you're gonna have that in. All right, if there are no other questions, you have a great weekend. I'll stay on the line for a couple minutes for anybody that has any questions. All right.
Yeah. Have a good day. Thank you.
All right, well, you too. We'll take it easy. We'll see you.
I have a question, but it's
Yeah.
not about the math material.
Uh-huh.
So I emailed you a couple of days ago. I figured I'd wait for you to respond and you never did, so I'm just gonna ask about it now. Um, so after I took the review chapter test, I got a really low score because I realized I forgot to reduce fractions on.
So are you referring to the review that I posted on Canvas?
No, the like actual quiz that we took.
Oh, you mean for chapter R?
Yeah.
Okay.
I figured I'd ask about it. Yeah, I got a 67% because I forgot to reduce fractions. I don't know. The other ones I got wrong just because I got them wrong, but I know on a couple of them, one of the, like an example of one that I got wrong, it was like 2b over ab, and the answer was 2 over a.
Let me see. So you had 2A over what, 2B, and the answer was A over
No,
B?
it was so that's basically like a good example of what I
Yeah.
was talking about.
All right.
I was just wondering if I could somehow get like half credit or something on
All
those
right.
questions.
Yeah, I mean, I can go back and look at some of those problems. What's your last name?
Gillian, Gillean.
Let me write that down here. Gillian.
I don't know how many that actually happened on, but I know it happened on at least one or two.
Okay. Okay, I'll go back and I'll just kind of look at that and maybe I can, slide you a couple points back. Okay.
If not, that's okay. But I figured it was worth an ask.
All righty. All right, I will definitely look into that. Okay.
Okay, thank you.
All righty. Yep.
Have a nice day.
You too.
Quick question about the
Yeah.
exam.
Mhm.
So for like the actual exam, I just want to make sure because my sister's she's been in college and done all this. Will I need to get like a recording like software or something for that? Or is it just like take it and get it done and
Yeah,
do
it's,
your
it's gonna be
best?
on Alex, so there's no special provision or anything. All right.
Okay, because
I-
I was gonna say I'll have to get a like software for that then, and I just wondered if I needed to.
No, there's gonna be about between 20 and 25 questions on the exam, and
Okay.
I'll make sure that I give you an appreciable amount of time to finish it up. But yeah, it has to be done by midnight, October 4th. Okay.
Okay, sweet. Thank you so much.
All right, have a good one.
You too.
Oh.